Welcome back to this video series on how to do quantum mechanics with programming. In today's video, we're going to be looking at the uncertainty principle and how we can verify that holds using programming. As always, if you like this video and would like to see more, then please comment, subscribe, like, and share with your friends. That helps it gain visibility. So, in the last video, I gave you the exercise of calculating x squared and p squared. So let's just start by solving those exercises. So in order to do that, I'm going to go back to the previous file and borrow the functions that we created in video 4. So we created this x hat function, and we also created the p hat function, which were the position and momentum operator. And I'm also going to import confit as CF, import numpy as NP, and then also let's create our system. CF.quantum mechanics 1, and then xlim -10 to 10. xres, and I also put xres to 100. The reason for that is if I don't specify that it's 100, then the wave packet is going to be slightly shifted. Doesn't really matter, right? Okay, so now let's borrow one of our functions. So we had this thing here, so that's what we're going to start with. So this is the function that we're going to be playing with a little bit. It's positioned slightly to the right, and it has an initial velocity of 0.5. So let's start by calculating x squared. So the integral that we need to calculate in this case is simple. I suppose that depends. But the integral we need to calculate is the integral of psi and then the x operator acting squared on psi, which is essentially the x operator acting twice on psi. And so to do that using our code, we write, so let's do x hat applied to qm.psi. And then I want to apply x hat to whatever I get out of this again. This is going to be my x squared. And then I need to multiply with the complex conjugate of psi. And then I need to integrate this whole thing over integrate field, this whole thing. And the result is 1.04. And then this additional imaginary part, which we're left with, again, because of the fact that we're using numerics, we're approximating, and so therefore there's always going to be like the small imaginary part, even though in theory this result should be a real number. So that's that. And then, of course, to calculate p squared, the calculation is the same. We just need to replace these two operators by p hat instead of x hat, and then we get something else, which is 0.49, blah, blah, blah. Okay. So the topic of this episode is to look at the uncertainty principle. And in order to understand the uncertainty principle, we need to understand what variance is. And so in statistics, this image is taken from Wikipedia. In statistics, the variance is how spread a distribution is. So here we're looking at two kind of distributions for an experiment or something, and they both have the same average, namely 100, but one of the distributions, it's much more spread than the first. And so what we say then is that the second distribution has a higher variance than the first. And to calculate the variance, you take the expectation value of x squared, the one we just calculated, and then you subtract the expectation value of x squared. And if you don't know why that is the case, you can go look at some tutorials and videos on YouTube that show how to derive this. But the what we call the standard deviation of this distribution then is the square root of this variance. So for our wave function, let's go now in and calculate the standard deviation for x. So we have our number here, which is the expectation value of x squared. Now, I'm also going to calculate the expectation value of x, which is this. And then I'm not going to apply the operator twice. I'm just going to apply it once. So here we have that. And so in order to calculate the variance, I need to take x squared, or the expectation value of x squared, minus the expectation value of x squared. And what is that, you ask? It's 1 exactly. That's nice. And it still has this imaginary part tacked onto it. Yeah, let's just keep it for now. So you see that I'm not hiding anything. And so the standard deviation in x is given by the square root of the variance of x, which is essentially just it's also going to be 1, I suppose. Yeah, 1. And then it's like this small imaginary component that's coming along since we're doing numerics. And the same expression is true for the variance and the standard deviation in momentum, right? So in momentum, we have p squared minus the expectation value of p squared. And so we can calculate that too. It's going to look very similar. So if I do the expectation value of p squared is equal to, you have to act with p twice on the expectation value like this. And then the expectation value of p is going to be just p applied to the psi field. And then we can calculate the variance in p as p squared minus the expectation value of p squared. And then finally, we can calculate the standard deviation in the momentum by taking the square root of the variance. So now we have delta x and delta p. And if I print delta p, I get this number here. So 0.495, blah, 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 plus minus 17. And the next thing we're going to do is we're going to try to calculate delta x times delta p for different psi's. So let's do that. So if I do now delta x, we already have one, right? So delta x, delta p is equal to, and then we get this number 0.495 something, something, something times, and then this imaginary part. Now, from this point on, I'm just going to take the real part because I don't want to watch this other part again. So here you can see the value is 0.495 something, something, something. Okay, so this was for this wave function here. So let's try to calculate this ratio for a different wave function. So I'm going to create this thing here, and then I need to calculate this, and I need to calculate, I should have done this in one block, I see. Then we calculate dx. And then let's do the same thing for p. I think I can just do this. So if you select the symbol and then you press D, it's going to like mark the next version of that symbol. So now I know that the only thing I need to change are these p's. Now I have both of those. and then I'm just going to print that the product of delta x and delta p is, and then this. And so this was the function that we started with before, and we got that the product of delta x and delta p is 0.495. If I change it somehow, let's say I make it double as wide. Actually, let's also print out the individual values. So delta x is delta x, and yes, you got it. Delta p is delta p. So you can see that, and also let's take the real part. So you can see that now when I've changed the width of the initial Gaussian to 2, then the change in the position is, or the standard deviation in the position is now 2, whereas the variance or the standard deviation in the momentum is now 0.25248, and the product is 0.49. And if I change it to something else, like 1 or 0.5, then again, I get different numbers, but the product is still about the same thing, 0.495. And what you will see here is that actually in this case for these Gaussian functions, the product is always going to be 0.5. And to get like a sense of what that means, I'm going to be plotting this function here. So let's start with this. So let's place that in the center, and then let's give it a width of 1 and an initial velocity of 1. I think I need to do fig x is equal to this, and then I'm going to do qm dot show fig. Guess not. Yes. Okay. So we're starting with this wave function here, and we see that delta x, meaning the uncertainty in the x position, is 1, which is like how wide this Gaussian wave function is. And we see that like, oh, if we measure this many times over, we're going to get a variance in where the position is. And we're also going to get different results for the momentum if we try to measure that momentum, and that's given by delta p. But the product of those two uncertainties is 0.487. Now, if I change this to be half as wide, we get an initial state, which is like a Gaussian, which is much more close together. It's much less spread out. And what happens then is that the uncertainty in the x position is decreasing. Now it's 0.5. If you look closely, it's almost exactly what I set it to. But the uncertainty in the momentum is increasing. So we're less certain about the momentum, but we're more certain about the position. But the product is still around 0.5. And so, and the other way around, if I make it very wide, like if I say that its width is 2, then you see that the now the position is less clear. So the standard deviation in the position is now 2, whereas the standard deviation in the momentum is more clear, because and the reason for that is that from an intuitive level, if you remember back to the plane waves, the momentum of a wave function is essentially equal to the if you look at a plane wave, it's essentially equal to the wave number, which dictates like how far is it from one red spot to the next. So this wavelength here. And the wider the wave function is, the more easy it is to accurately define what is the wave number of this wave function, but at the same time it sort of spreads out. And that is essentially the uncertainty principle. It tells you that if you have a wave function which is spread out, then it's easier to determine the velocity of that wave function, but it's less easy to determine the position. And the other way around, if it's very sharp, like if let's say I set the width to 0.1, then the position is going to be very clear, but it's very hard to determine what is the the phase gradient in this. So you can see that here, you get that the variance in x is 0.09, whereas the variance in delta p is 3.7. So it's very unclear, and the product is actually 0.30. Now, the uncertainty principle states that the product of these two uncertainties, delta p and delta x, is always supposed to be larger than h bar divided by 2. Now, in our case, h bar is equal to 1, which means that the uncertainty principle from this numerical point of view says that the uncertainty in delta or delta x multiplied by delta p should always be larger than 0.5. And in fact, that is not exactly what we see. Like, we see that we got 0.3 here, which is not true according to the uncertainty relation. But the reason for that is that this is numerics, and so as you can see, like, yes, I have claimed that this is a Gaussian function, but because of the limited resolution of my system, it doesn't actually look like a Gaussian. So if I were to do this again, and now I bring with me these numbers and I create the system anew, and then I increase the resolution to 1,000, for instance, then you can see that, first of all, the function is going to look much smoother. We're coming. Yeah, so the function now looks much smoother, right? Looks like a proper Gaussian. And now you can see that the product of delta x and delta p is much closer to 0.5 again. And if I were to increase the resolution even more, then I would get a more accurate result. Now, the other thing that's interesting about this is that the uncertainty principle states that the product of these two is supposed to be greater than or equal to 0.5 times h bar. For a Gaussian wave function such as this is actually the sort of ultimate wave function in sort of it's the wave function that has the least amount of uncertainty in it. So, for instance, if I created something else, like, let's say I create a different wave function, how do I do that? Well, I can say qm.psi is equal to, and then there's a function called calc Gaussian. So I'm going to put this Gaussian at position -1. Just bear with me for a moment. And I'm just going to scale it by 0.5 so that it's normalizable. And then I'm going to add a second part of this wave function at position 3. And of course, I want this to be normalized. So I'm going to take the square root of these two. And then I'm going to just multiply. So this is how you do it. And then I'm going to multiply by just a phase just to get something interesting. So qm.psi is equal to qm.psi times, and then I'm just going to, just add this complex. Just to add a velocity of 0.5. Like this. And I also need, so this is just a fact. If you want to evolve things later on, you can't just like set the initial condition like this. You also need to specify what is the Fourier transform of this thing, but that's for the next video. So I'm just going to write it like this for now. And then I'm going to cover it more in the next video. But if I do this now and plot this, you can see that now I'm starting with a completely different wave function. The resolution is still 1,000. So also, I think that they might be quite wide, these wave functions. Yeah, these were quite wide. Also, I wanted 3. So let's do 3 and width equal to 1. Width equal to 1. And also let's reduce the resolution here to 200, just so we don't need 1000. So now I see that now I have a different wave function. It still integrates to 1, but now if I calculate the variance in the x position and the variance in the momentum, then you can see that the product of delta x and delta p is actually larger than 0.6, larger than 0.5, which means that the uncertainty principle holds, and it's just in case of these Gaussian functions that it's actually equal to 0.5. And so that's the uncertainty principle from a numerical point of view. So for the next video, I would like to try to see if you can calculate the Fourier transformation of psi. Look up the relevant functions, see if you can figure it out, and then I will see you in the next episode.